Mike Peardon here today, visiting from Trinity College in Dublin. And Mike will tell us about searching for exotic hadronic states with charm quarks.
Thank you very much. Thank you very much for the invitation. Pleasure to be here. Yes, so today I'd like to tell you about a long and ongoing story looking at strong interaction, so definitely going to stick with the standard model today. And essentially looking at the problem in spectroscopy, looking really for exotic hadronic states, seeing whether they can be observed cleanly in experimental data. And the focus today is on charm quarks, because that seems to be a very good place to really try to disentangle this physics and to understand what's going on. So this is work done in collaboration with a list of characters. You can see that most of the work was done by Christopher Thomas, who's now in Cambridge, and Graham, a graduate student who's just moved to become a postdoc in Fulmer Tower. But there's a long list of people involved at various stages, and there's two publications, one on charmonium spectroscopy and one on D&D mesons, which you can refer to if you'd like to understand the detail. So here's what I'd like to talk about today. So in order to understand a little bit what we mean by exotic, then of course we have to understand what's meant by not exotic, and that's basically defined by the good old quark model. And then what happened over the past 10 years or so is, driven by experimental discoveries, there's been a renaissance really in spectroscopy and charmonium. If you'd talked about charmonium spectroscopy, say 15 years ago, then really it seemed to be completely solved, and it was just clear that the quark model explained everything. But then, when the B factory switched on, they started observing states above the open charm threshold, and the states just most definitely didn't fit into this very simple picture. So there was a renaissance then, a renewed interest in strong interaction in physics in these exotic states, driven purely by experimental discovery, laid at the B factories. And now it's ongoing as well. There's more work being done at LHCb, for example. So, for example, JPC, the spin quantum numbers of the X3872, the most famous of these new states, were recently resolved by LHCb, in fact. So again, other experiments have got involved as well. So I'm going to describe a lattice calculation, trying to make a contribution to understanding what's going on, what these newly discovered states look like internally. And so let me try to explain a little bit about what we're going to need in our lattice toolkit in order to do excited state spectroscopy. So we obviously want to look high up in the spectrum. And so I'll explain what we need to put into our calculations to be able to do that. Then a little bit about the techniques we've developed to hopefully meet those requirements. And then show you the results, then, essentially, of our current status of our analysis. And then this work, like I say, is continuing, and what I will finish up with then is looking at scattering. So obviously, since all of these new discoveries were states that were above the open charm threshold, so that they can decay into a D and a D bar meson, in order to understand them in detail, we obviously need to understand something about those decays, so that means understand this scattering. So let's start off very gently and write down the simplest picture we can of a meson, which is just a quark and an anti-quark, maybe in some potential, but they're in orbit around each other. And the quarks are spin 1/2, so the total intrinsic spin then, if you like, is 0 or 1, so they can either be a spin singlet or triplet, depending on their spin alignments. And so the total angular momentum is just then, you can also have some orbital angular momentum about some axis. And so the total momentum is the sum of those two things in this model. And we have parity in charge conjugation if this is a charm quark and a charm anti-quark. We have charge conjugation. That's good quantum numbers as well. And if you just go through the very simple calculation to understand the allowed parity and charge conjugation quantum numbers that you get when you have the spin singlet or spin triplet combinations, and you tick off the allowed JPC combinations, then you find that there are some missing, some that are inaccessible. And those are quantum numbers then that are called spin exotic. And this is almost complete, actually missing one. The 0 minus minus is also spin exotic. But you find the ones that are missing are basically any j value that's even with PC plus minus, or odd with PC parity charge conjugation minus plus. So there's no way of combining this very simple system and getting, say, for example, 1 minus plus quantum numbers. So it's just inaccessible in this system. So that would be a very nice signature then of something happening which is physics that's not described in this system.
Sorry, in the case of the scalars, it could be pseudoscalar glucose. Pseudoscalar glucose would be actually something called an exotic number.
A pseudoscalar would be 0 minus plus. That's
Right.
That's not. That's allowed.
Okay. So
Definitely, that's the most
Yeah,
non-exotic
right.
quantum number you can think
Right.
of.
So, but then which one?
But that's not on this list. Right. That's not exotic. Then. 0 minus plus is most definitely not exotic. No. That's the least exotic quantum number you can think of. So 0 minus minus is exotic, and also 0 plus minus. But of course we know that the quark model is not the end of the story. Obviously there's the QCD, and we can have, here's a nice cartoon of other ways of combining quarks and gluons. So of course in QCD we have gluons as well, which complicate the picture, and making color singlets. So the rules of QCD are supposed to be that confinement tells us that you have to have an eigenstate of the Hamiltonian, we need something that's colorless. But there are lots of ways of getting at that, obviously, not just mesons and baryons, which are sort of factored into the simple quark model, but you can also make combinations where you have quark and an anti-quark, but also some intrinsic gluonic excitation. So you put the quark and an anti-quark into an octet of color, and then neutralize that with the octet of color of the gluon. Alternatively, you can put 2 anti-quarks and 2 quarks together, 2 Q bars and 2 Qs together, and the ways of contracting the indices that are sort of non-trivial, and make what's then called a tetraquark. Or you can essentially, just glue together 2 mesons, essentially, bind them perhaps by some. This line here is meant to perhaps represent just pion exchange interactions between these things. Perhaps if they get closer together, there'll be more complicated interactions. But you can imagine one meson in orbit around another one, if you like, in some more complicated state, and that would be then called a molecule. And then, of course, there are gluons as well. You can actually take two gluons and combine the tensor product of the irreducible representations of SU3 color into again a singlet. There's a singlet contribution to that irreducible decomposition. And then, of course, you might ask, well, what's the difference between these things here? They essentially have the same sort of Fock-based content, and there's not really a very clear distinction, in fact, but it's supposed to be a physics difference. It's really supposed to be a meson at one location, and a long way off there's supposed to be another meson, and they're just exchanging pions to stay bound. So typically in models that try to understand these molecular states, these are very close to thresholds of the mass of the meson plus the mass of the other meson plus some small correction, whereas these can be quite different. Here, really, you're expecting all of those 4 things to be close together inside one of these tetraquark states. So obviously there's more to the, and of course we'll simply introduce this set of allowed states into our recipe and look at the allowed JPC values, and we quickly find that we can fill in those gaps as well. So we can get spin exotic quantum numbers in QCD. So QCD allows for those spin exotic quantum numbers. So they're only exotic in the quark model, if we restrict ourselves to this picture, but they're not exotic in QCD. QCD allows them if these states are really dynamically allowed by QCD. So as advertised, about 10 years ago, a little bit more than 10 years ago now, then there was this renaissance, this rediscovery of interest in the charmonium spectrum. Those discoveries were made in the B factories, and they discovered lots of new bumps essentially above the open charm threshold, and they get these names X, Ys, and Zs. And there's now about 20 of them, or something like that. Some of them are obviously a bit more well established than others. But the most famous ones, the ones you'll hear discussed most, are the X3872, which has really got a lot of experimental interest. There's lots of papers written about this over the past 10 years. It's extremely close to the mass to the mass of a d meson plus a d star bar. So if you just look these two masses up in the PDG and add them together, you basically get 3872. And in fact, experimentally, the mass difference between the X3872, this bump, this structure, and this threshold is not experimentally determined. So it's 0 with an experimental error. So it's sitting right on the threshold. And this is a very narrow resonance as well. And again, as far as I know, the width hasn't actually been resolved accurately either. So the width isn't really known. And so this is a very, generated a lot of heat, if you like, a lot of interest. And so that's certainly one thing that we're hoping to look at in the near future. I won't tell you much about it today, but it's on our to-do list.
Sorry, can I insist on the nomenclature? According to the old quark model, right, so you still can have 4 quark states. There's nothing wrong with that. It's being color
right, it is, right.
Color flavor forces are not for that. They were actually we started with these things, right?
So I call it a simple quark model. So I didn't. Yeah,
so
that's right.
Your definition of quark model is this 3 in other words, having actually quark and anti-quark.
Yes,
But, I mean,
that's right.
You know, since the dawn of physics, they were already predicting these 4 quark states.
Yeah, absolutely. Yeah,
So in that sense, it's not much exotic.
It's exotic in that extremely simplest possible picture of a meson.
But that was, they've been about newts, right?
Absolutely, absolutely, yeah, absolutely. Yeah, I'm not absolutely. That's right. That's all I mean by exotic. I mean, I just don't mean it's not exotic in QCD. So QCD is not. There's nothing forbidden by 1 minus plus quantum numbers in QCD. That's right. So again, there have been more and more of these discoveries, and then of particular interest are these Z plus states. So there's one at 4430 that's the most well observed, cleanly observed, if you like. And this is something that it looks like it intrinsically contains charm quark and a charm anti-quark. By its decay properties, it certainly looks that way. But obviously it can't just be that, because it's got an electric charge. And so this is the state that's discussed then most when we talk about tetraquarks. But again, still some debate about what the internal structure is. And then there's lots more. Like I said, there's been a renaissance, there's been lots and lots of these things being found. And presumably, as the experiments work harder and harder at these things, then perhaps some of these will turn out to be the same thing, and some of these will go away. Who knows? But at the moment there's something like 20, depending on where you stop counting, of these unexplained resonance structures. Structures in the experimental data above the open charm threshold. And there's not really a very clear picture that's emerged regarding what these things are as well. So we'd like to see if we can use lattice QCD to say something.
Sorry, for the same token, I mean, also, as we know, we also have not 900, I mean, there's even before the charm threshold, you already have potentially for quark states like the F0 980, right? Which is presumably an SS bar state, but again, it cannot decay into KK bar, and therefore it's relatively narrow. That is exactly the same type of KK star, only used by KK star.
Right, so so I'm going to talk mostly today about stuff around 4GeV. That's right, yeah. I mean, so of course, all of these exotic states can exist in the light meson spectrum as well. But there it's even harder, perhaps, to disentangle what's going on with all of those states, because there's lots and lots of quite broad resonances down in that one.
The F0 980 is extremely narrow.
Yes, but there's lots of other resonances there as well that are quite broad as well. So it's a very much muddier area to study.
It's identical. I mean, extended F0 980 is an azo triplet. Sorry, an azo singlet, and then there's an A0 980 which is an azo triplet.
Absolutely, yeah, that's absolutely, yeah. But the experimental picture is just much muddier, much cleaner here up in the charmonium spectrum, because generally speaking, you've got states that are narrow compared to the widths are very different energy scales compared to these excitation scales in general. So it's experimentally a bit cleaner, certainly, and hopefully perhaps theoretically a bit cleaner as well. The light meson spectrum is certainly very, very interesting, and all of this stuff, all of this physics will be happening down there as well, but it's even harder to disentangle what's going on down there. So let's see if we can start with what's possibly the cleanest laboratory, which is this set of data that's come out of these experiments. And you know, there's certainly a lot of experimental data here to look at as well, so it's certainly a very rich place where hopefully theory input can meet experiment. So I've just taken this picture from a recent review article which Steve Olson wrote, which is very nice, and it summarizes the picture, maybe since I'm going to run out of time if I go through it. It's just basically a sort of quick cartoon view of what I've just been talking about. So here's the D star energy scale. That's the X3872. That's certainly one of those interesting states. JPC was identified unambiguously by LHCb last year, 1++ quantum numbers. But there are also other, across these range of quantum numbers that are experimentally the nicest ones to look at, there are these funny pink boxes of states that don't really naturally fit into sort of this quark model picture, if you like. And the quark model picture is sort of like these yellow states. And these grey states as well, I'm sorry, which are the undiscovered quark model states, if you like. So there's definitely stuff that doesn't really fit into that very simple picture of charmonium. And also, like I say, there are these charged states as well. These sort of purple boxes are some of those charged states that have been observed. So, okay, so can we help disentangle this picture with lattice QCD? What are the technical requirements? So obviously we've got to be able to study excitation spectra, not just ground states of these systems.
On the previous slide, you were saying the end products, are you saying those were discovered and didn't know what they were, or you're saying those are predicted by theory?
Yeah. Okay. So all right. So the yellow boxes are the established sort of things that fit very neatly into this simple quark picture of you have a potential, you have a quark and an anti-quark, and you just solve a Schrödinger equation basically when you're obviously the model's a bit fancier than that, but that's the simplest starting point. That would predict this spectrum of yellow boxes and grey boxes as well. Now, some of those have been observed experimentally. There's the yellow boxes. Other ones are predicted by that simple picture. Those are the grey boxes. They haven't really been cleanly discerned experimentally.
And the red boxes are predicted?
No, the red boxes are the experimental discoveries, these X, Y, Z states that don't really naturally match up with the simple QQ bar plus potential with relativistic corrections and so on. I mean, it's not that simple. Yeah. So this is the pattern, of grey and yellow boxes in this review. You can look at the details. Would be what you get from that sort of simple quark model of a potential plus charm quark and anti-quark with relativistic corrections. And you see that these states that there's an overcounting, and there's states that don't fit into that pattern very well at all. So there's extra states here in the 1-minus channel. Extra states here in the pseudoscalar channel 2, where you would only expect to see 1 in this mass range from that simple picture, and right the way across you see states that don't really fit very neatly. The yellow and grey boxes don't line up with the pink and purple. So something else is going on. That's really what this picture is supposed to be saying. Okay, so what do we need to put into our lattice calculations in order to hopefully contribute something useful? So first of all, like I say, we've got to be able to study excited states. These aren't ground states in any of these spin channels. We've got to be able to make sure that we can make a link with the continuum, and I'll come back to this point in a little while, and identify the continuum quantum numbers of the states we study on the lattice reliably. We've got to be able to use operators which have overlap on these interesting states now. So for example, if one of these particular states really looks like a tetraquark, then we've got to have an operator that looks like a tetraquark as well. That seems to be what's come out of our analysis as well as being fairly crucial. So we've got to be able to put those into our calculations as well. And then of course all of these states, where this disagreement between the experimental data and this simple sort of quark model picture, it's all above these open charm thresholds. They start here. Here's twice the mass of the d meson, and here's d plus d star. So these are the open charm thresholds. Below that, the picture's much more straightforward, and really the experimental data matches up with this simple quark model predictions. And all the quark model states have been seen and nothing else. So all of the interesting stuff is happening above in the top half of this picture. Below is quiet and easy to understand. And of course, everything that's above these lines can then decay into dd bar or dd bar star. So we've got to be able to study decay, and that means, of course, decay to dd bar, which means, of course, we want to be able to understand dd bar scattering and see whether these states appear as resonances in a sort of theoretical calculation of the properties of dd bar scattering. And then we've also got to hopefully get control of our usual systematics from our lattice calculations. Lattice volume, discretization effects, the effects of perhaps not getting the quark masses right, and so on. So today I'm going to basically spend most of the next half an hour or so looking at the first two, and hopefully I will then discuss progress of the remaining three points on this list. So we're working our way steadily down this list, making slow and steady progress, and hopefully eventually we'll get to the bottom of this list and be able to say something of interest. So we're not there yet, but we're hopefully moving slowly down this list, this to-do list. And the first issue is what makes this notion of studying decays complicated is because in order to do our calculations, we want to study the path integral on the lattice numerically. And to do that, we're going to use Monte Carlo simulation. And in order to make any progress, we have to use an importance sampling algorithm. And those importance sampling algorithms need a non-negative weight. And so the only way to get that is to first, instead of working a Minkowski space-time metric, the real world, we have to study QCD on a Euclidean space-time. So this is a requirement in order to do Monte Carlo simulation. Now it turns, and then of course that means that dynamical information about scattering is lost. Direct information is lost. So we'll have to find another way to get to understand scattering. But actually, it turns out to be actually a useful thing as well, as a mechanism of getting the low-lying spectrum of the system, ground state and excitations. Being in a Euclidean spacetime is actually useful. It actually defines a way of projecting onto the ground state and low-lying states easily. So it's actually beneficial in some sense. The problem, like I say, is scattering is much more complicated, and so we have to find a roundabout route to get there. And we can get ground states very easily, but we can also get ground state, the lowest lying part of the spectrum straightforwardly by adding in variational methods. So I'll come to that in a second. And here's how that works. If you're in a Euclidean spacetime, and we measure a two-point function of a creation operator and an annihilation operator separated by some time t, and then it's a straightforward exercise to insert complete sets of states and so on and so forth, and you find that this correlation function looks like a sum of exponentials with positive weights. And notice these are exponentials, not phase factors here. So these are exponentially decaying factors rather than phases. And so that means that if we wanted to measure ground state energy, we would just measure this two-point function, take the limit of this separation going to infinity, and then we find that this should fall off exponentially with the rate of fall off being the ground state energy in that particular channel. So that obviously whatever energy we get depends on the quantum numbers of this insertion operator, of course. So like I say, going to Euclidean spacetime is actually very useful if we're interested in getting isolated from ground state. So this works as a sort of projection operator onto the ground state very usefully, which we wouldn't have, of course, in Minkowski method. Then if we want to get more than just ground states, it's been known for a long, long time now how to go beyond this. And the idea is basically to write down some basis of operators all with the same quantum number, and think of operators which are formed from linear combinations of those basis operators. And that then is the idea of the variational calculation. And so now if we can extend our two-point function and can compute all possible correlations between all elements in our basis, so let's suppose we have n of these operators. If we can measure all n squared possible combinations and form this correlation matrix, then with that matrix we can solve this generalized eigenvalue problem, and now it turns out in this limit here that t becomes large again, the kth eigenvalue is linked, gives us information about the kth energy level now. So kth doesn't just have to be ground state energy. If we have a big basis here, then we can get ground state for this excited state and so on. We can start looking higher up in the spectrum as well. So we can solve the problem then of measuring beyond ground state energies in this Euclidean metric by constructing this correlation matrix. I mean, of course, for this to work, then we need to make sure we've got a good basis in that sense. I mean, it really needs to have good overlap onto the states that we're interested in. And we've also got to be able to do this calculation. We ought to be able to measure all elements of this correlation matrix straightforwardly, hopefully, which is a non-trivial thing in a lattice calculation. And if you want to see the detail, there's a very nice paper by Bossier et al., which really goes into this detail very nicely. So if you're interested in the details of those calculations, I recommend you look at that paper. Okay, so if we can measure this thing here, then we can hopefully not just get ground state information in our Euclidean space-time calculation, but we can also look at excitation spectra as well. Next issue is the one of making spin identification. And obviously in the continuum, three-dimensional space has a rotation group, O3 or SO3, a Lie group. But as soon as we put space-time onto a lattice, our regulator will break that down to just a cubic point group. So on the lattice, instead of having JPC as a quantum number, we have a set of states which will be classified by a sort of a quantum letter now. So obviously, rather than having an infinite tower of irreducible representations of this Lie group, we're going to have just one of a limited set of possible irreducible representations. So it's a finite group, so it has a finite set of representations, irreducible representations. And those are the irreducible representations of OH. We want to make sure that we can undo this, understand the link between these two symmetries cleanly when we're doing these calculations. So in its simplest manifestation, our lattice operators will form states that transform irreducibly under this quantum letter R, which is labeled an irreducible representation of this smaller group OH. And so this group has 5 conjugacy classes. So if we put parity in, there are 10. And we see then it's a group with 24 elements, so that with a little bit of maths, you can see that we have to have a set of irreducible representations that look like this. So we have to have 2 one-dimensional irreducible representations, a 2-dimensional irreducible representation, and 2 3-dimensional irreducible representations, and that's it. So we don't have an infinite tower of irreducible representations, spin states that go up to infinity. We just have 5 irreducible representations, and that's the extent of it. So what's the link between continuum spin and this lattice quantum letter? This lattice irreducible representation. Well, to get at that, you have to understand how the irreducible representations of O3 subduce into OH, and you have to make tables like these. Now this is a table that does go all the way down to infinity that way, and it's linking the continuum spin quantum number with this irreducible representation on the lattice. So the trivial representation in the continuum is the trivial representation on the lattice. That's easy. Vector representation, again, is T1 with this 3-dimensional representation. Here's the vector representation, the fundamental representation of OH. But as soon as we get to spin 2, you see already something complicated happens. if we were to identify a continuum spin 2 state, then what we should be looking for in our lattice calculation are two states in two distinct channels. And so the 5 polarizations of a tensor spin 2 state in the continuum should be split across a 2-dimensional and a 3-dimensional irreducible representation on the lattice. And from there on all the way down, every irreducible representation from there on is then split in this way. So spin 3 appears across 3 irreducible representations, 4 across 4, and it just gets dense, more and more dense as we go down. So the question is it enough to search for, just look for these degeneracy patterns? And unfortunately, certainly if we're looking at charmonium, then the short answer is no. I mean, nature sort of plays a slightly cruel trick on us actually, because if we look at the p-wave triplet states, 0 plus plus 1 plus plus 2 plus plus, the chi-c0, chi-c1, chi-c2 states of charmonium, then, and they're almost degenerate of course, so we would expect to find a set of states that are nearly degenerate in the continuum with these quantum numbers, a spin 0 state, spin 1 state. And if you look at what that corresponds to in this lattice data, you see that we would end up with a 1 here, nothing in this column, a 1, a 1, and a 1, if we added up those first 3 rows. And that's exactly the same pattern as we have here in spin 4. So if we find a set of degenerate states in the A1, the E, the T1, and the T2, can we necessarily distinguish that between spin 4 from spin 0, 1, and 2? And the answer is not really very cleanly. So it would be nice to be able to do better than just this pattern matching. And the trick that we found that works very well, I won't go into the details, is essentially to make sure that you construct the operators with one eye on the continuum limiter, if you like. So you start in the continuum with an operator that looks like a bunch of covariant derivatives inserted in a bilinear. There's an example here. This can be extended to tetraquarks and so on and so forth. But here I'm just considering a simple bilinear operator. So start in the continuum, where obviously we can reduce this to reduce representations of the continuum rotation group, so we get J spin quantum numbers. And then once you've done that, subduce those representations to OH. And then as a last step, replace the derivatives that I have in this expression with their lattice versions. So following those steps, then we have some memory at least, hopefully, of the continuum symmetries built into our lattice operators. So, probably don't have time to go through the detail here. Here's just an example. If you imagine we wanted to create a spin 2 state, like the chi-c2 in charmonium, then this would be the continuum operator that we'd write down. That would be irreducible under that rotation. You see it's a symmetric tensor, traceless symmetric tensor. And then we replace these derivatives here, these single derivatives in this case here, it's a p-wave state, with lattice derivatives. And then we find now we have lattice operators. And we find that they split as advertised across the E, this 2-dimensional representation, and the T2. But we have hopefully a little bit more information, and we can look at matrix elements, overlaps essentially, of these operators onto states. And if we can find something like a symmetry between them, then hopefully that means we might be able to say that we've identified a spin 2 state in the continuum. And I'll show you some data in a little while. Okay, very quickly now before I show you the results, again, let's go back to this notion of scattering. And so there's a theorem that tells us that basically the scattering matrix elements we'd like to compute, such as you'd write down thinking about scattering in the continuum, are just inaccessible in the Euclidean quantum field theory description. And that's, like I said, we use this to our advantage to give ourselves a projection operator onto the ground state, but that also means then, of course, that this object here doesn't look like a scattering matrix in the same way. At large T, this looks sort of basically like a rank 1 operator that just projects into the ground state. So this link here is missing. But there's a way around it. It's what's called the Lucia formalism, is at least the starting point for this whole story. And back in the late 80s, Lucia showed that essentially we could find information about elastic scattering elastic scattering by looking at the spectrum of the system in Euclidean space-time and looking for its volume dependence. So what we need to be able to do is we need to be able to compute the spectrum of our system as a function of hopefully different lattice volumes and see how the spectrum evolves as we change the box size. And if we can do that in detail, this recipe tells us then how to slightly indirectly infer information about elastic scattering. So that will work from the elastic threshold up to any inelastic thresholds as well. So it doesn't say anything about inelastic scattering. So extending this is sort of a work in progress, if you like. But in order to do this, we need to see sort of fairly small shifts in energy in our spectrum. And remember, we've got already the sort of complicated job of measuring excitation spectra as well. And so we're going to, again, need precision and resolution. And we also need to be able to put in the right operators as well. So we also need to be able to put in things that look like the decay states of these X3872 or whatever it is into dB bar star or something like that. So now it's already starting to look rather complicated. So we need good precision from a Monte Carlo calculation. We need to be able to put in this very complicated operator basis. And we need to be able to resolve all of these energy levels. And if we can do that, then there's now a recipe that allows us to get at elastic scattering information.
So that means that I can't really get access, for example, to an elasticity parameters. Like if I have to scatter like pi to pi k, I cannot really do that. Typically that is inelastic.
Not using Lucius formalism, no, that's right. But there are extensions that are being worked on now to try to do that shit. But there doesn't seem to be at the moment, doesn't seem to be a model-independent way of doing that. So you have to perhaps do some modelling. But yeah, that's a long discussion for another day. But that's a work in progress, if you like. Yeah. So I mean, in its simplest form, the Lucius formalism just describes elastic scattering. If you want to talk about a couple channel, or 3-body, or 4-body, then you certainly for the foreseeable future will have to perhaps do some modelling. Hopefully, the answers will not be too model dependent. Okay, here's a very simple toy picture of what I mean, just to explain that again. Let's take this very, very simple toy Hamiltonian, which I'm pretending describes some heavy particle with mass m, and two massless pions as the final state, and we're just varying a box size in one dimension. And there's some coupling constant that links those two states, which is just this parameter g. So this is a trivial toy model. And if we just look at the eigenvalues of this 2x2 matrix, if g was set to 0, then obviously we would get one state that would fall off like 1 over L. So obviously, why is this 1 over L factor coming in? That's basically because we have a finite box with periodic boundary conditions, so the momenta of the decay products, these two pions in this model, are quantized. These are integer values by the boundary conditions. So the allowed momenta are integer times 1 over L. So this 2-hadron system, this pi-pi system, with a total momentum of 0, or any total momentum, has a discrete spectrum rather than a continuum. And if they've got the same quantum numbers as this hypothetical particle that I've introduced in my toy, then QCD can mix those states. And it's that mixing that basically causes the decay of this heavy particle into pi-pi. So you can see why it's the same physics that describes decay is describing the energy dependence of this spectrum. So now if we switch on this interaction, we see there's an avoided level crossing. And as I change the box size on the x-axis, my energy spectrum gets a more complicated shape. And where this 1 over L would have crossed the mass of this resonance state, if you like, that's where those energy levels, instead of crossing now, they push apart. And the amount by which they push apart gives you information on this coupling constant. So if you can see how much these energy levels shift as we move the box size, we can infer this constant here and sort of learn something about the decay. So that's just a very, very simple-minded toy picture of what's going on. Okay, so now I've written down this very long wish list of things that we want to put into our lattice calculation. And we've worked very hard at coming up with a solution which would enable us to make these calculations. And the solution is this trick which we've called distillation. So those of you who aren't lattice aficionados, I've already fallen asleep. I'm going to spend about 5 minutes just on this technical stuff. Feel free to have a little snooze, and I'll talk very loudly when I'm done, and we'll get the results soon enough. So this is the technical bit. So feel free to stare out the window for a few minutes. The trick is basically this. What turns out to work very nicely is if we redefine smearing. So smearing is sort of a fairly essential ingredient in hadronic physics, trying to create good operators that look like hadrons. In a hadron, the quarks are smeared. They're not localized. They're in some sort of blob, which has some scale to it. And that's been well understood for a long time by lattice physicists, and they use it as a good method to write down good operators that project onto ground states. So smearing is just a linear operator, which has some spatial structure really, that you apply to the raw quark fields in the path integral to make smeared fields. And it's a good way of getting the infrared degrees of freedom, if you like, the real long-range structure that really is a sort of confinement scale physics. And then, rather than making a creation operator for a meson by sandwiching some other operator in a bilinear side bar psi, directly where these bilinears are directly the path integral variables, we would use instead these smeared fields to write down our operator. So before we write down a bilinear that we're going to compute the 2-point function of to measure the spectrum, we'd add this extra step in between where we smear the fields. And that's been, like I say, been known for a long, long time as a very effective way to get to the low-lying energy eigenstates much more effectively. And these overlaps of these smeared operators are usually much higher than if we hadn't done this smearing trick. And so, like I say, if we think about that smearing and redefining smearing, can we use a different definition of smearing, which has all the same sort of essential properties, to help us with this long list of things that we want to be able to do this charmonium project and other projects? And it turns out the answer is yes, we can. If we think about the sort of more traditional way of doing smearing, what we would do is basically write down an operator, which is where we take the gauge covariant Laplace operator, exponentiate it with some parameter sigma there, and that defines this smearing operator. So that's the sort of Gaussian smearing. So it makes a blob which has got some scale set by this parameter sigma. It's gauge covariant because we plugged into this exponentiation, we plugged in the gauge covariant Laplace operator, and that's a very common way of doing smearing. Turns out if you look at the spectrum of that operator, so just feed it into some eigenvalue evaluation code. So here's some data from a lattice. This is going back a few years. It's a very modest size now, which is 16 cubed spatial volume. This factor 3 is just for the 3 colors. You can see it's an operator that's acting in some rank 12,000 vector space. So there are 12,000 eigenvectors. And here in this plot, I've plotted them out in order, so smallest to largest. And you see I've plotted it in a deliberately obscure way, because actually all of those, so it starts at 1 and it falls off extremely rapidly. You probably can't see it, but there's a little green blob here, which is the spectrum. And you see it occupies a tiny amount of this space. So it has support in a really small part of this vector space. If we blow up this small portion down here and look at the first 200 modes, you see that it's fallen off. After 200 modes, it's fallen off by 2 orders of magnitude. It just keeps on falling. So this smearing is an operator that sort of obliterates almost all of the degrees of freedom in your quark field. So that's a very useful observation. And in fact, let's go one step further and actually define our smearing operator to be a projection operator into this low-rank vector space, a vector space of order 100 rather than order 10,000. So let's recognize that what smearing does is essentially wipe out almost all of the degrees of freedom in the quark field and expose a very small set which are important for hadronic physics. And actually really write smearing down as a projection operator. And so we've wildly simplified the problem of creating good hadron creation operators. We've recognized that we don't need to worry about this enormous vector space of quark fields on a lattice. We just need to work with this much more modest sized vector space, which you've got an order of 100 rather than an order of 10,000 degrees of freedom in it. And just to show you this operator is sensible, it's got all the gauge covariance properties you want, and it looks roughly spherically symmetric as well. It has sensible continuum properties. There's just a nice picture of one of these eigenmodes of the Laplace operator. You see that it has in it sort of confinement scales in it, so you can see we get blobs if we look at the eigenmodes of the Laplace operator, which are roughly a half or one Fermi across. So you see confinement in those eigenmodes already. So it's doing something sensible. The point being now that a hard problem of constructing this two-point function, where I want to insert arbitrarily complicated operators in here with those derivatives so I can create high spin states, factorizes into a problem of determining properties of much, much smaller matrices. And that's this trick that we've been exploiting very aggressively to do all of our physics measurements. So let's go move on to results. Here's the list of things that we haven't done right. Before I show you results, just put my cards on the table if you like. So the pions are heavy in these simulations, about 400 MeV. We have some more data now, so we'll be going to lighter pion masses in the near future. So far, in the data I'm going to show you for the charmonium spectrum and d-meson spectrum, we haven't included those two meson operators. I'll show you some slides at the end where they are included, where we're starting to look at scattering. But certainly for the next 5 minutes or so, you won't see those two meson operators in the basis. I've also dropped these extra contributions for the disconnected charm. That's a whole other seminar perhaps, so I won't describe that too much. And this is all done at a single lattice spacing, so these are not in the continuum yet. So just to show you the variational calculations working, here's some data. Let's not worry too much about it. If anybody wants to see the details, they can go to the paper. And also, to show you this spin identification that I very quickly described is working, let's look at it as an example. If we look in this PC minus minus T1 irreducible representation, so that's the fundamental representation of the cubic point group. In this calculation, we could write down 26 operators if we consider in the continuum up to 3 derivatives and subduce. And let's order those into a block of things which would look in the continuum like spin 1 states, like spin 1 operators, spin 3 and spin 4. And let's plot one time slice of that correlation matrix, so 26 by 26 matrix that I'm forced to measure if I want to do this variational calculation. And what we see is this block diagonal structure emerges between the operators that would be spin 1 in the continuum, spin 3 in the continuum, and spin 4 in the continuum. And then the off-diagonal pieces are much smaller. So small numbers here in these off-diagonal blocks, big numbers are restricted to these diagonal blocks. And that tells us that this spin separation that we were hoping for is working quite effectively in charmonium physics. So I don't have so much time. So again, we have to then start pulling apart these overlaps. They give us lots and lots of information. Here, as we look up in the spectrum for each eigenstate of the Hamiltonian now, which has an energy, we can also look in a bit more detail as to which operators contributed to creating it. So when we look at these eigenvectors, of course, we get a list of 26 numbers that tell us which operators really contributed to that state. And hopefully, again, that enables us to label the states with a spin in the continuum. So we have spin 1 here with these big red bars. The ground state is spin 1. So there's the first excited state and the second, and now you see we have lots of big blue bars in this fourth excited state in this channel. So that's a spin 3 state, and you can go all the way up in the spectrum, and then eventually you find also a spin 4 state there as well. And then I can then look across different irreducible representations and identify at the same energy, in these different irreducible representations, I can find all of the polarizations of a spin 3 state, or a spin 2 state, or, the color coding there is wrong, I'm sorry. Yellow should be spin 3. Yeah, there's colors that got mixed up there, I'm sorry about that. Anyway, trust me, it does work out if you look at it properly. I'm sorry I mislabeled that slide. And then again, we can look for this residual symmetry across different states that would have there's no apparent lattice symmetry that relates these matrix elements. It would be this continuum symmetry if we could find this pattern. And then sure enough, we find that there are indeed these operator matrix elements on the lattice do indeed line up across different lattice irreducible representations. So there's no lattice symmetry reason why these numbers should be the same, but because of this continuum link, which we think is working out properly, enabling us to do continuum spin identification, we do find similarities across these distinct lattice areas. So spin identification works out for us. Just keep that. So here's the spectrum from our calculation. Now remember, the most important thing that's missing in this calculation so far are those two meson states. So everything that's above the interesting stuff, if you like, that's above the open charm threshold is still not right. So we still have to work on this part, but nevertheless we start to see interesting patterns emerge. So first of all, of course, we get the stable, well, the stuff that's below the open charm threshold we get right, pretty much. There's some discrepancies which are due to lattice artifacts and quark mass mismatch and so on. And then above the spectrum, again, we're still able to identify stuff which fits with the quark model. So here's our sort of 1s state. We also see 2s. We see the 1p and the 2p as well. Spectrum. So quark model-like states appear. Then the D wave is there. And then also F wave and so on. And those are states now which are predicted in the quark model above the threshold. So we are starting to resolve them. But we also start to see lots of extra stuff appearing in this interesting energy range here, which is about 4.5 GeV. So we are starting to see things that don't fit into these quark model patterns. And of course, as a sort of smoking gun of that, across here, right in this rightmost column, 1 minus plus, 0 plus minus, 2 plus minus, those are spin exotic quantum numbers. So we're resolving states in the charmonium spectrum, again in that interesting regime, 4.5 GeV, 4 GeV, somewhere right there, where all those XYZ states are sitting. We're starting to resolve states which have these so-called spin exotic quantum numbers. And so those are coming out of a QCD calculation, of course. This is not a quark model. And we can look in a little bit more detail at these states. Because we've used derivative operators, we can take pairs of derivative operators and create something that looks like essentially like F mu nu, that looks like a B field, if we just consider its spatial components. And that's something that you can think of in a sort of constituent model as creating a gluon, if you like. So these are sort of operators that excite an intrinsic gluon, perhaps. I mean, that statement doesn't really have a very precise definition, but you can see what I mean by it. And again, those states are up there in that experimentally interesting region there, about 4.2 GeV or thereabouts. And again, they form multiplets, much like the states in the quark model do, including spin exotic components. So 1 minus plus has partners in 2 minus plus, 0 minus plus. That's the triplet, and 1 minus minus as well. And then with 3 derivative operators as well, there's another whole set of states, again with these quantum numbers, including some spin exotic combinations like 2 plus minus.
So just to be sure, so these dark bands are the experimental values? Or?
That's right, yeah, so these dark bands are experimental. So that's right, yeah. Yeah, including some of those Y states in the 1 minus minus. And obviously the 1 minus minus is, of course, the one that's best mapped out in E plus E minus colliders. So there's lots of stuff there. So the fact that there aren't there aren't experimental states all the way across here is just that they haven't been seen. So this is just the states that have been seen. Well, since I'm running out of time, I won't go into the detail here. So we've looked a little bit about seeing if we can control our lattice artifacts. And that's definitely still a work in progress, but we've looked all the way across the spectrum, and by changing our lattice discretization, we can at least get some handle on the size of those artifacts in our calculation. So first of all, just by looking at the hyperfine splitting between the E to C and J psi ground state, the right answer is 118 or whatever it is, MeV. In our calculation, we get an answer that's quite a way off that, about 80. But if we dial up a particular term in our lattice action, then we can reproduce the right answer. And then if we look at the rest of the spectrum with that boost to that particular operator in action, we can see how much the spectrum moves around. And right the way across, including some of these spin exotic states, we can do that measurement, and we can see how much these more interesting states that we really want to nail down, how much they move. And again, they move about the same amount all the way across the spectrum. There's a scale of about shifts of about 40 MeV. So that's about the typical scale of our uncertainty at the moment, is of order 40 MeV. So we look all the way across the spectrum. We change this parameter in the action that should give us some handle on the lattice artifacts, and we find shifts of order 40 MeV. So we can at least put a sort of rough scale on our uncertainties there. So I'm running out of time, so there's d-meson spectrum done as well. And again, we see a tower of states. We're able to repeat the whole calculation there. There are, of course, some experimentally interesting states, including the 0+ channel, which is sort of a little bit, doesn't fit terribly well with simple models. So there's some interesting physics to learn about there. Also the d sub s 0+ state is interesting, because it sits actually below the threshold for decay. And so we're looking at that too. And once again, by looking at the operators, we see that as we look up in the spectrum about 1 GeV above the ground state, we start to see states that, again, will be missing in a very simple QPR picture of D and DS mesons. So again, there are sort of something that looks like hybrid excitations in these spectra as well. Oops, going the wrong way, sorry. So in my last remaining 2 minutes, let me move on to the what we're currently working on. I'm making slow and steady progress on, and that's understanding scattering of charm mesons. So as a warm-up exercise, we're looking at scattering a pion off a D meson. And we're doing a very uninteresting, if you like, from the experimental point of view, channel. That's looking at this in isospin 3/2, so the maximum isospin. So pion has isospin 1, D meson has isospin 1/2. So there's obviously isospin 1/2 and 3/2 as a combination of d pi, possible channels of d pi scattering, and we're looking at the sort of least interesting one, if you like, the 3/2. And this is just to get our technology set up. It makes life a lot simpler when you don't have resonances. So there's no resonances expected in this channel, so that obviously simplifies our calculation. So all we need to look at is sort of d pi scattering, and it can't form a resonance, or at least it would be very strange if it did. So what we do is, here we've so far done 2 lattice volumes. So this is the lattice size in units of the spatial lattice spacing. So there's a volume of 20 cubed, 24 cubed. And again, we've measured a spectrum of states by constructing these operators using this distillation trick that look like, make a state which has got total momentum 0. And that could look like a D meson at rest and a pion at rest. That's these states here. Or it can look like a D meson with 1 unit of momentum and a pion with 1 unit of momentum in the opposite direction. And so we put all of those states into our basis, do the variational calculation, and see that these are our spectrum of that comes out in these boxes. And we see then we get these blue lines, obviously the 1/L predictions that you would just get from if there was no interaction between D and pi. So you can see we're looking for these small shifts away from the non-interacting levels, but nevertheless our precision is good enough now to start resolving those shifts. So we can see shifts away from the non-interacting lines. And because we get shifts away from the non-interacting lines, that means that the D and the pi interact. So these energy levels move around. And it's those interactions, those energy shifts, which will also cause, of course, a phase shift in the experimental data. And that's what we can then use the Lucia formula in order to translate these energy shifts. So we measure these energy differences, drop them into the Lucia formula, and from that we can infer a phase shift as a function of energy in the center of mass. And so sure enough, these phase shifts are all negative, and there's a rather mild energy dependence to this phase shift. And that's just telling you then, of course, that this channel here is repulsive scattering, sort of as expected. So there's obviously no resonance here. Instead, there's a sort of mildly repulsive interaction between d and pi in the isospin 3/2 channel. And that's consistent with what's known experimentally.
So in principle, if I use, I know it's not perfect, but if I use the heavy quark symmetry, it should be also equal to pi d star. Because the d star and the general state.
Well, except that's got an intrinsic spin for the meson.
Very different, but you can relate them, right?
Right, probably, yeah.
Yeah, so because we can use the heavy quark competitive to actually extrapolate forward. So this can become a prediction for the d star.
So this is S-wave scattering. So yeah, you would have S-wave scattering of d star pi S-wave scattering. Yeah, that's right. So this is S-wave scattering.
Right.
But that's right. Yeah.
And then you could basically use that as a prediction for the atom.
Yeah, I guess that's right. Yeah.
I mean, if this, of course, if this were an actual B meson, that would be even better. Right?
Right.
But I mean, if you do it in B, then you can actually use that basically as a prediction for the D star. Then you can
D
independent
star
check.
pi. Yeah. Yeah, I think that's right. Yeah. Okay, so this is, like I said, a first step, and it's this direction. Like I said, there's no resonances here, so the number from a spectroscopy point of view, it's not so interesting. But nevertheless, it's nice to see that we can actually resolve a phase shift from this analysis.
Well,
And like,
I think you wrote it down. I mean, if this could be found, would be correct to D star rho.
that's d star rho would be yeah, because you need to get the spin quantum numbers right. Yeah, so S wave d star rho is d star rho 2 vectors, so you can get total angular momentum 0 out of that. So d star pi wouldn't have the right quantum numbers in S wave. It would be a vector. You spin 1 over all of it. So this is an inelastic threshold that opens. You have to, of course, be careful to recognize the Lucia formula only works up in inelastic thresholds. So these inelastic thresholds are marked on this plot here. So I guess you should not take that point too seriously. It happens. It looks sensible, but you know, everything above these inelastic thresholds, then strictly speaking, the Lucia formula doesn't work. Okay, I'm out of time, so let me just finish up. So we've made a lot of progress, hopefully getting towards building a toolkit that would allow us to study charmonium states in the interesting experimental range of 4 to 4.5 GeV, which is where all these new XYZ states are popping up, and that's so mysterious. We're able to identify spin, which was an important sort of technical point. We find that excitations that look like hybrid mesons have emerged out of our calculations, but we still have to recognize that we seem to get out what we put in a little bit, so that we don't have anything that looks like a tetraquark yet, because we haven't put that in into our operator bases. So that's, again, something we have to work on. This distillation trick that we developed for these calculations is working nicely, works nicely for charmonium as well as the light hadron spectrum. And so what we're working on now is adding in some more operators that look like tetraquark combinations, maybe that look like molecules, and we're not really doing much on that at the minute, but tetraquarks are something we are working on. And then also mixing in these multi-hadron operators to do scattering properly and get these spectra that we can use for studying resonant behavior. And then there's, of course, a bunch of other things we have to get under control as well. So hopefully we'll be able to say something about what's happening in the charmonium spectrum, what those XYZ states are in the not too distant future, but we're not there yet. We still have to solve a lot of technical and physics problems before we're done. Thanks for your attention.
Questions? Yeah.
I mean, sorry to go back to the messy one, but I mean, there's been also a lot of scattering studies of the light to just understand that those should be the light version of this scattering. Do you have any comment about that? I mean, we'll be looking at those.
Yeah, there's. I mean,
a lot of comments whether the molecules
I mean, I wouldn't. I don't think that it's. I don't think that the calculations are mature enough to make really very. They're in their infancy. I mean, I think this whole field in lattice QCD of doing these scattering calculations is very new. I wouldn't really say that you could take any calculation that's been done to date and say that really has got a real insight into the final answer isn't there yet. But I mean, it's definitely seems to be rolling along very well. The frame, there's a lot that's still to be done. Just technical stuff. Also, the formalism has to be extended so that we can study inelastic, and the paper's now on looking at 3-pi scattering. So Hansen and Sharp have a paper recently which looks at that, and then understanding coupled channel stuff. So my collaborators at JLab are starting to do some coupled channel stuff. K-pi is looking very nice. They have a really good looking set of data there. They understand K-pi and K-eta coupled channel very nicely. Again, it's the technology that we've developed here works very nicely in the light hadron spectrum world as well. So I think these ideas will translate between those two worlds. But to date, I don't think there's a calculation that you can really say they're done.
That's great.
Yeah.
So maybe actually what can just ask, what about the sigma just to us?
The sigma is very hard.
chance,
Yeah, the sigma is it's just it's an incredibly broad structure, pi, S-wave, vacuum quantum numbers. It's got all the bad things going for it, right? So it's the worst, the hardest one to do. So it's not been done, in a way that I would say is definitive yet. I mean, there are groups working on it.
Potentially possible? I mean, or is it ruled out?
Sorry?
Is it potentially possible? I mean, is it
Yeah, I mean, you have to.
foreseeably possible?
I mean, there's a lot. All of the problems are there. So it's a very difficult one. But yes, I mean, it's give us a few more years, and we'll see what we can do. Yeah,
I cannot leave always give us more years.
Yeah, right.
Lattice has got a lot of years.
Yeah.
You got to do it even faster now.
I mean, I think it's.
It will be
But you
great.
could imagine investigating the quark structure of the sigma, or the structure with this method.
You can imagine it. Yeah.
Well, I can even imagine it.
Yeah.
Besides the mesons, there's also the hadrons.
Right.
So I'm actually promising that during my thesis I was studying how to link the heavy quark Lagrange, heavy metal Lagrange, to the heavy solitons, and therefore you can get with the same coupling of the scatterings of these the actual masses and splitting masses of the heavy body. Because you can do that. So basically, we're actually different from the quark model. You have an infinite number of states, so you cannot really complain. Even the exotic ones, right? The things about the solid Lagrange that you can give an infinite number of states, not only that. And you can do a crank procedure, basically the predictions that relates the heavy scattering, DD star and the DD star scattering with binding effectors. You can actually turn that into precise predictions for the difference in masses of the hadrons.
Okay.
So the question I'm asking, how far are we with the hadrons with the spectrum loops?
Yes. So I mean, there's technical problems doing calculations with baryons efficiently, which we're still struggling with. So there's not. I mean,
Even to calculate the spectrum.
Oh, I mean, the spectrum just using sort of 2-point functions are just with 3-quark insertions and not with any multi-hadron states. I mean, those have been done, but none of the scattering calculations. So obviously that's the big missing part of this.
I think that has been missed. It's the beauty of that the spectrum of heavy bindings related to the scattering of the mesons to large N and large N. So that actually you have any implicit predictions of the spectrum coming, or the clipping of the spectrum coming from the scattering data.
Yeah. Okay. Yeah.
So actually, so you can in principle also relate this to in principle the independent computation.
Okay. Yeah.
In the same way, like the heavy solitons, you get the mass of the proton from the scattering of the binds.
You're right.
You can do that.
Okay.
But use this advantage. Again, it should be more rigorous than implicitly because you have now two large means, one large N, which is according to Witten is large enough, and equal to 3. And the other one is the large M, which of course it should work better for the B mesons than it is for the charm mesons.
Right.
But until then, given that I can see three rough predictions from the lattice, perhaps not too bad, rather than comparing to the lattice would be necessary to the work model, would be nice to compare to the Stirm model, because that is actually better under control.
Yeah.
But I can give you the reference.
Yeah, no, interesting. I'd like to see that. Yeah, baryons, I don't know, which sort of make even slower progress just because for technical reasons, just for calculation reasons, numerical reasons rather than certainly lots of interesting calculations to do. They're on the to-do list, but they are moving even slower just for technical reasons, for computational numerical reasons, not interesting reasons.
Yeah.
So this distillation method, the number of eigenvalues of the Laplacian you have to compute. How does that scale towards the continuum limit?
It doesn't depend on the lattice spacing, it just depends on the volume.
So it's not a v square.
It depends on V, the volume, and not on A. It's infrared, it's just, you can think of it as physics, right? So if you change the cutoff, you make more modes, but you throw those ones away, because those are all a cutoff scale modes. So as you go to the continuum limit, there are more and more modes up at the high end of the spectrum that you're throwing away. The number of modes at the low end of the spectrum that you need to keep would just grow as you increase the volume. The volume just the
So they grow as V.
So it grows with V and doesn't depend on A. After first approximation. So the continuum limit is not a problem. The infinite volume limit is. Yeah.
Okay, so if I keep the volume fixed and I go to the continuum limit, then it becomes v square.
No, stays V. It doesn't change. You wouldn't notice the continuum limit there. You'd just be throwing away even more. It just gets more and more efficient. You're throwing away more and more stuff. Just keeping a smaller. You keep a fixed number of modes.
So I keep the number of modes fixed. I don't keep a cutoff like 100 MeV fixed.
Yeah, well that's the same. Right? That is the same essentially.
Well, but I know that the number of modes then.
It's the infrared end, right? So you put a cutoff at the infrared end, but that's the volume. And if you change the ultraviolet cutoff, it doesn't change.
But the number of modes within that cutoff.
The fraction of the number of modes you're keeping is changing, but the actual number of modes is staying fixed. So you're just throwing away more and more, but that doesn't matter, right? You're throwing them away. So. Yeah, I mean, you sort of need to keep, say, if you have a box that's 2 Fermi across, then you need to keep 50 modes or something like that. Regardless of, even in the continuum limit, that would still be true. Yeah. To the extent we understand it, I mean, it's not. The experiment hasn't been done, so maybe there's a surprise waiting for us. But that's.
Yeah, because you would expect the gap among modes to decrease with the volume. So
with the volume, yes.
So you would expect you should keep more. Keep a cutoff, a physical cutoff.
With the physical volume in physical units.
Any other questions? If not, let's thank Mike again.